All right, we want to prove that if a squared is invertible, then that must mean that a is also invertible. As a refresher, this must mean that A is a square n by n matrix, because the question of invertibility is one that only applies to square matrices to begin with. So A is n by n, then A squared, which is just A multiplied by itself, is also an n by n matrix. And so what we're asked to show is that if A squared is invertible, then A must also be invertible. And what I want to do here is use this as an opportunity to tie together several related concepts, that is, the idea of a null space, the idea of a determinant, the idea of invertibility in general, all in proving that this statement is true. So we're going to prove that this statement is true in three different ways. First, we're going to prove that A is invertible by construction. In other words, we're just going to find its inverse. And if we can find it, well, that must mean it exists. The second way is we're going to argue using the null spaces of A and A squared. And the third way is that we are going to look at the determinants of these matrices. The first way requires the most work, by construction. What do I mean by that? First, let's look at the fact that A squared is invertible. What does that mean? Well, then it means that there exists some other matrix, let's call it, I don't know, B, such that A squared B is equal to the identity matrix, where B is the inverse of A squared. Okay? That's what it means that A squared is invertible. But if we just look at what's on the page here and realize that A squared is just AA, then this also says that AAB is the identity as well. And look what we have here. It looks like we found another matrix that we can multiply A by to get the identity. And what does it mean for A to be invertible? It means there exists some other matrix, A inverse, such that AA inverse is the identity. So are we done? Can we just say, yes, A is invertible and its inverse is AB? Not quite. It seems tempting to just stop there and say, okay, we're done. A is invertible because we found its inverse and it's AB. But that's not, what we've done so far isn't sufficient. And remember, it's because the inverse needs to be able to be multiplied in both directions. And here, in finding the inverse of A, all I've done is I've started with A squared B is the identity, where B is the inverse of A squared. But notice, if I instead of using that expansion, I wrote BA squared equals the identity, I would have found a different inverse for A. What do I mean? So here, I said B is the inverse of A squared, meaning A squared B should be the identity. Here I'm saying the same thing. B is the inverse of A squared, but I've just multiplied in the other direction, or in the other order. Okay, and both of these should be true if B is the inverse of A squared. What does this mean? Well, it means BA, BAA, is the identity as well. And if I did this, well, then I would say, hey, the inverse of A is BA. Because I multiplied A by BA and I got the identity. And so the question is, which is it? Is A inverse AB or is it BA? Remember, in general, for two arbitrary matrices A and B, A times B is not the same as B times A. So which one of these is the inverse of A? I'm not sure. Well, it turns out AB and BA are equal in this case. Again, in general, for arbitrary A's and B's, they're not. But here they are equal. And to be fully rigorous, I want to show that here A and B are equal. Or sorry, not A and B are equal, but AB and BA are equal. How am I going to do this? Well, why don't I start with BA? And here what I can do perfectly legally is multiply this by the identity matrix. So BA is equal to BAI, where I is the identity. But here I have several equivalent versions of the identity matrix, right? BA squared is the identity, and A squared B is also the identity. So let's pick, I don't know, A squared B. This is also true. But if I expand this out a little bit, this looks like BA. Now this gives me two more A's, B. Okay? Now what do I notice now? Now that I've expanded out the three A's in the middle, here this BAA is also equal to the identity. What does that mean? Well, it means that this whole thing is the identity times AB, which is just AB. What that means is that here BA and AB are the same matrix, okay, which is something we need to justify in order to be fully confident that AB is the inverse of A. Turns out that AB and BA are the same matrix and they're both the inverse of A, and since we've constructed them, then by construction, A is invertible, and these are its inverse. Okay, so that was one way of proving that A squared being invertible proves that A is invertible too, and we found A's inverse by using A squared's inverse, which we call B here. The next way I want to prove this involves thinking about the null spaces of A squared and A. And from a proof technique perspective, I want to use what's called a proof by contradiction. Totally fine if you haven't heard of this idea before. But the general idea is that I'm going to assume the statement is false. So I'm going to assume that this statement is not true, and I will show that that leads to some sort of contradiction or something nonsensical, which means if we work backwards, this statement must be true. Okay, because if it's not true, then something impossible happens. So here, what is the opposite of this statement? That is, what would be true if this was false? Well, the opposite of this statement is that A squared is invertible, but A isn't. So let's start by assuming that that's the case. Let's live in this universe for a second. Well, if A isn't invertible, what does that tell us? Well, this tells us several things. It tells us A's columns aren't linearly independent. It tells us A's rows aren't linearly independent. It tells us that A's rank is less than n. It also tells us that its null space is not the trivial null space. That means that there are vectors other than the zero vector that when you multiply them by A, you get the zero vector. So I'll say there exists a non-zero vector x such that AX, where again x is not the zero vector, gives you the zero vector. Okay? But what can I do here? A perfectly legal operation is to multiply both sides by A squared and check out what happens when I do that. When I multiply both sides here by A squared, that gives me, sorry, not by A squared, but by A, because multiplying by A will unlock the A squared. Multiply A here and an A here. What does this give me? Well, here, this will give me an A squared x, because I had an A before, I added another one. And on the right, A times the zero vector is still going to be the zero vector. What is this saying? Well, it's saying x, if it was in the null space of A, it's also in the null space of A squared. So if AX equals 0, then A squared x also has to be 0. But conceptually, what does this mean? Well, it means that x is in the null space of A squared. But what this is saying is that there's a non-zero vector in the null space of A squared, which means A squared's columns aren't linearly independent either, because I found a linear combination of them that gives me the zero vector. That linear combination comes from looking at the components of x. So it's impossible for this to be false. Because if this were false, meaning if this statement were true, then we lead to this contradiction, right? It's impossible for A squared to be invertible, but A not to be, because if A wasn't, then it would have a non-trivial vector in its null space, but then that vector, that non-trivial vector, would be in A squared's null space too, leading to this contradiction. So this statement here is impossible, which means it must be the case that if A squared is invertible, then so is A. So that was the null space-based argument. And the final argument comes from looking at determinants. Okay, and this is perhaps the simplest computationally, but maybe hides a lot of the conceptual understanding of what's going on here, which is why I'm putting it last. So the key fact is that the determinant of a product, so the determinant of AB, is in general equal to the determinant of A times the determinant of B. Okay? So the fact that A squared is invertible means that the determinant of A squared isn't 0. Okay? But the determinant of a squared is the determinant of a times a. That's not 0. But using that fact, I can separate this into two separate determinants. Determinant of a, determinant of a. Okay? But this is just the determinant of a squared. Okay? What this is telling me is that the determinant of a also can't be 0. Right? The idea is that if a squared's determinant isn't 0, well then a's determinant, which is just the square root of a squared's determinant, also can't be 0. Okay? All right, and also this implies, assuming we're working with real valued matrices, which we have been in this class, that a squared's determinant is actually positive because a's determinant is the square root of that, as we can see here, and it can't, you can't take the square root of a negative number when you're working with the reals. Okay, so the argument here was that a squared's determinant is just the square of a's determinant, and if this is not 0, then its square root can't be 0 either, meaning, and remember, a matrix is invertible as long as its determinant is not 0. Since neither of these matrices have a determinant of 0, it must again then be true that if a squared is invertible, then a is invertible too. Okay, so that was our third and final proof of the fact that if a squared is invertible, then a is invertible too. And hopefully all three of these different arguments gave you different ways of thinking about the same idea, which is invertibility, but hopefully this showed you the various ways in which these ideas over the past few weeks of the course fit together.